Hi, I'm Ryan, and today I'll be presenting Cerebro, a platform for cryptographic collaborative learning. This is joint work with Weikeng, Weikeng, Panda, Raluca, and Jan. Let's start with a use case, which is anti-money laundering. A bank wants to detect and prevent money laundering using machine learning, as getting it right is of critical importance to them. However, money laundering is often difficult to detect by a single bank because criminals try to conceal their illegal activities across many banks. Therefore, the banks would like to come together and compute a machine learning model over their joint data to be able to detect such money laundering that occurs across many banks. However, they currently cannot do so as they cannot share their private data with each other due to privacy concerns and competitive reasons. In fact, many other applications can be enabled by data sharing, but currently none of them can happen as the data in question is sensitive and people are unwilling or unable to share such data for collaborative computation. The main question then is, how do we allow organizations to share data for collaboration without showing the data in plain text? Well, one technique in cryptography that is great for this setting is known as secure multi-party computation, or MPC for short. It allows the parties to emulate a trusted third party through cryptography, and it provides the security guarantees that no party learns any information beyond the final result. Great, let's say the banks are impressed with MPC and want to deploy it into production. Let's say they decide to run decision tree inference, and they put Alice, who works at one of these banks, in charge of this secure collaboration. What are some of the challenges she might run into? Well, a couple challenges include balancing generality and performance, and balancing privacy and transparency. And we'll go over these challenges in more detail over the next few slides. Let's first talk about balancing generality and performance. So Alice wants to run decision tree inference. She has two options as to what type of MPC protocol she can deploy. The first option is to use a specialized solution, and the second option is to use a generic solution. For the first option, she can use a hand-tuned MPC protocol for her specific task. She goes and reads a bunch of MPC papers, but finds that these protocols are specialized for particular models and deployment settings, none of which fit her exact needs. Therefore, while these protocols can be very efficient, they're not generalizable to all types of settings and use cases. Okay, so that option didn't quite work out, so she tries the second option of using a generic MPC framework instead. Speeds and AgMPC are two state-of-the-art frameworks, and she does some research into these and finds that there are many protocols and even sub-protocols to choose from in these MPC frameworks. Some examples are shown here on screen. Each of these protocols has its own performance trade-offs. Therefore, while this option provides generic functionality, it's difficult to use efficiently as not knowing the trade-offs and picking the wrong set of protocols to use can result in inefficient execution. Now that we talked about the first challenge, let's look at the second challenge of balancing privacy and transparency. So while MPC ensures that the input data remains private, this also means that participants like Alice lose some control over the computation. They cannot reason about the quality of data provided by other participants or about the quality of the model before it's released. This can reduce incentives for parties to participate in this collaboration and overall increases their risk when using MPC. We address this challenge through two mechanisms: policies and auditing. Policies occurs before a model is released, whereas auditing occurs afterwards. Let's first talk about policies. Alice works at a bank, which is competing with the other banks in this collaboration. Therefore, Alice worries that her competitors might benefit more than her from this collaboration. For example, let's say this green bank has relatively low quality input data, while the other two banks have relatively high quality input data, which we denote using the accuracy of a model trained only on their local data. Let's say they participate in this collaboration, they provide their data to the secure computation, and receive a model trained over their joint data. And we see that while the green bank benefits from this collaboration, the other two banks do not. Therefore, there needs to be a way for participants like Alice to enforce certain policies within the secure computation so that they're incentivized to participate in the collaboration. In fact, there are many more policies parties may want enforced in the computation, such as limiting the amount of information a model leaks about its underlying training data, and ensuring that the model meets a minimum performance threshold to ensure the collaboration is worthwhile. Now that we talked about policies, let's talk about auditing, which occurs after a model has been released to the parties. So now let's say the banks receive the resulting model from their collaboration, and Alice deploys the model into production. Let's say that she observes a series of mispredictions, such as mispredicting a stop sign, and begins to suspect that a backdoor has been inserted into the model. Alice would like to audit other parties' private data to figure out the source of the problem. In this case, how do we trace back the bad data to the source, especially in the context of secure computation, in which the input data used to train the model is kept private? We introduce Cerebro, an end-to-end platform for secure collaborative learning. We operate in the n-party dishonest majority setting, and we protect against either semi-honest or malicious adversaries. We address the two main challenges we discussed before, balancing generality and performance, and balancing privacy and transparency. And we achieve this through our techniques. We address the first challenge through our DSL and MPC compiler, and we address the second challenge through our release policies and auditing framework. We'll focus on the MPC compiler in this talk, and for a more detailed overview of our other techniques, please reference our paper. There are two notable contributions in our MPC compiler. The first is automatically partitioning a program into a local precompute, which consists of operations that can be done by a party on its own private data in plaintext, and global compute, which consists of the remaining operations that must be done in secure MPC, which is much more expensive. The second contribution is optimizing MPC protocols based on the layout of the parties. Due to the time constraints of the talk, we'll focus on the second contribution. To explain this optimization, we'll use the semi-honest triple generation protocol adapted from Speeds as an example. This protocol consists of 2 rounds, but since each round does roughly the same thing, we'll go over only 1 round for simplicity. In each round, each party has its own randomness, which they encrypt, and then they designate one of the parties to be an aggregator. The aggregator receives the ciphertext from the other parties, and then aggregates them, in this case adds the randomness using homomorphic encryption, and distributes the result back to the parties. Now, let's start with this protocol again, but now let's imagine that these parties now reside in different regions. The green and the blue bank are on the west coast of the United States, and the gray and the orange bank are now in Europe. And let's say that the connection within each region is rather fast at multiple gigabits per second, while the connection between the two regions is over an order of magnitude slower at 100 megabits per second. Now let's run through this original protocol again. So each party begins by sending their encrypted randomness to the aggregator. And in this case, we notice that the green and the blue bank in particular have to send their encrypted randomness over this very slow cross-continental connection. And as I mentioned before, the protocol consists of 2 rounds of interaction. And if you run this protocol many times, the performance hit of sending data over this slow connection is significant. Therefore, we optimize this protocol by introducing a different hierarchical version of the protocol. And our insight is that in addition to the global aggregator from before, we introduce a regional aggregator for each region that aggregates the data of parties in its own region. So instead now, each party will send its encrypted randomness to their regional aggregator over this fast intra-region connection. Each regional aggregator will then aggregate these results to produce an intermediate result. Then they'll send over their intermediate results to the global aggregator. The global aggregator will aggregate these intermediate results to produce the same final result as before in the baseline protocol. And this result is sent back to each regional aggregator, who then distributes it to parties in its own region. And we see that in this simple example, this slow cross-continental connection is only traversed twice in the hierarchical version rather than 4 times in the baseline protocol. This improvement is further magnified if there are more regions or more parties within each region. Finally, I'm going to show a selection of our evaluation. Again, for the full evaluation, you can reference our paper. First, we'll look at the impact of our physical layout optimizations, as we just discussed. In our experiment, we had 12 parties in 2 regions, with 9 parties in one region and 3 parties in the other. We had a fast 2 gigabit connection within each region, and we varied the total bandwidth across the regions. We evaluated our 2-layer hierarchical protocol in which each region has its own aggregator against the baseline flat protocol in which is a single global aggregator that all the parties talk to. And we see that our 2-layer hierarchical protocol performs up to 3.5 times better than the baseline protocol. And this shows that if we consider the physical layout of parties in MPC protocols, which hasn't been done before, there are significant performance gains to be had. Finally, we'll look at the effectiveness of our planner's decision making, specifically the performance improvement of our physical planning when compared to the worst case secure plan generated without Cerebro. We evaluated this on many applications. We'll show the decision tree inference protocol here due to time constraints. And we see that as we varied the number of parties in this experiment, and we see that in the beginning, Boolean MPC outperforms arithmetic MPC up until this phase shift at around 9 parties, in which arithmetic MPC then outperforms Boolean MPC. This is due to the better scaling behavior of arithmetic MPC, and our planner incorporating the scaling behavior in its cost models for both frameworks is able to correctly predict the best performing framework to use in each instance of this graph. And we also see that making the wrong decision or choosing the wrong set of protocols to use for a particular task can have significant performance penalties. In conclusion, Cerebro is a programmable, secure, collaborative learning platform. It addresses the challenges that arise when deploying secure MPC in practice. Our source code can be found here, and we hope that you use it when deploying your MPC applications. And my contact information if you have any further questions. Thank you.